Hi, my name is Kang-Hoon Choi. I'm from Fraunhofer Institute of Photonics Microsystems, which reside in Dresden, Germany. I would like to present what you have done recently, which is about the effective cone rounding corrections in the data preparations for electron beam lithographies. From now on for 10 to 11 minutes, what I'm going to demonstrate can be summarized like these three. First one, we would like to present the analyzed and propose of the cone rounding correction method. And based on the first, second, we would like to show you the limits and ability of these cone rounding corrections, which means how far we can go, how much we are able to do that. And the last one is, based on the first two, what is needed, what is required and demanded for the future application, especially in the cone rounding corrections. That is, requisites of the cone rounding corrections in the data preparation. Before we start the analysis and the propose of the cone rounding correction method, we have to define the cone rounding itself. As you can see in the figures, the cone rounding can be defined as a ratio between the diagonal round and the maximum diagonals. The maximum diagonal round is defined as the diagonal critical dimensions of the design contact hole, which is a square. And the minimum diagonal rounds, when the exposed pattern is getting round around and formed out as a circle, is the diameter is exactly as design CDs, is the minimum diagonal round. So our cone rounding definition is the ratio between these measured diagonal CDs and the maximum diagonal round, which in between 0.71 and 1. The reason why I define this kind of a cone rounding as an inner cone rounding is based on our major applications. Recently, we have faced a lot of applications from our customers, which is more focused and interested in the inner cone rounding. Based on this definition of the cone rounding, we have tested the 4 different correction methods, as you can see in these figures. First one is some general standard method we have normally used. And second one is cross cone rounding correction we have developed, which consists of 2 additional supplementary shots on top of the basic designs. And third one is assist corrections, which also based on our previous studies, adding up of 4 corner shots inside of our design. And the last one is a serif corrections, which is normally have used in before. As you can see on these figures, when the design CD is decreased from 100 nanometers to 50 nanometers, all the figures has quite in accordance between the exposed images and simulation contours. But what you have recognized in here is that when the design CD is smaller than 50 nanometers, none of the correction method is properly working, which means that exposed image and simulation contour is well matched as some circular forms. Based on the qualitative comparisons between the exposed images and the simulation contours, we have a quantitative analysis of the cone roundings according to the different correction method. That result is appeared on these 2 graphs. The left one is the measured simulation result, and the right one is the result from the CDSAM measurements from the exposed images. As you can see, the left and right graphs was quite in accordance with each other's, and the green standard correction has also certain capabilities of the cone rounding corrections compared with the other, such as assist and serif corrections. Among the 4 corrections, the cross correction has better performances, less of the 3 corrections, and it starts to losing its capabilities from the design CD of 90 nanometers. This one gives us certain messages, that is, whatever the method and whatever the correction technique we have applied, from the design CD of 90 nanometers, we have to apply the corrections of the corner roundings anyhow. And not only this kind of quantitative and qualitative accuracies of the correction analysis, we have to take into account of the real practical facts, that is a writing time, which can be simplified as a shot count of the corrected pattern. The comparison of the shot counts appeared like this. On the left side of the images, from the bottom to the top, you can visualize the comparison of the simulation and exposure design is standard, cross, assist, and serif corrections, and these numbers gave you the shot counts. These shot counts can be counted of entire test pattern and visualized on the right side of the images. Normalized on the shot count of the standard corrections, cross and assist serif corrections is increasing its shot counts, which means it is able to increase its writing time. But cross correction also shows a better performances on rest of the threes, and it also can suppress the increase of the shot counts, the increasing of the writing time. So in this proposal of the cross corrections, we have balanced of the correction accuracies and the shot counts, which means writing time. As I have summarized, in the first, we have proposed an analysis of 4 different corner rounding correction methods, and we have found the cross corner rounding corrections performs better than rest of the 3. And these corner rounding corrections also having some improvements, need improvements from the design CDs of 90 nanometers. And not only the correction accuracies, but also in a real application point of view, we have shown the cross corner rounding correction method can balance the correction accuracies and its writing time. So now what we are going to do is embedding and implementing a fine model-based cross correction into our product, into the product of InScale, which is currently developing in Ascertain Nanographics, which reside in Grenoble, France. Thanks for having me, and then when you have much more further informations or collaborations, just call us. Then we, the Fraunhofer eBeam CNT and Ascertain Nanographics, will be with you to help you out, and we can find a solution together. Thank you very much.